Look up at the night sky. What do you see? A handful of glittering stars, perhaps a planet or two, and the vast, silent darkness stretching endlessly beyond. But what if I told you that this serene view is just the surface of a cosmic ocean teeming with mysteries so bizarre they defy explanation? The universe is not just vast, it's alive with phenomena that leave even the sharpest scientific minds scratching their heads. We've sent probes to distant planets, built telescopes powerful enough to peer back in time, and yet the deeper we look, the more questions we uncover. Strange signals, unexplained structures, celestial objects behaving in ways that break every rule we thought we knew. These aren't just anomalies, they're cosmic riddles waiting to be solved. Take a moment to picture this. Somewhere out there, a star pulses with a rhythm no astronomer can decode. A galaxy spins too fast, held together by invisible hands. A signal from the void repeats with mathematical precision, as if something or someone is trying to speak to us across the chasm of space. These aren't plot twists from a sci-fi novel. They're real, documented mysteries hiding in plain sight, tucked between the constellations we've known for centuries. And the craziest part, for every one of these enigmas we've stumbled upon, there are countless others lurking in the shadows, untouched and unexplained. That's where this journey begins. Today, we're diving into 30 of the most baffling, mind-bending phenomena in deep space, the kind that make scientists pause mid-equation and wonder if they've missed something fundamental about how the universe works. From rogue planets hurtling through the void alone to cosmic explosions that shouldn't be possible, each of these mysteries is a piece of a puzzle we're only just starting to assemble. Some might hint at new laws of physics. Others could rewrite the story of our cosmos altogether, and who knows, one of them might just hold the key to answering the biggest question of all: are we truly alone out here? Buckle up, because the universe is about to get a whole lot stranger. Somewhere in the depths of space, hidden behind the thick veil of our own Milky Way, an invisible force tugs at thousands of galaxies like a cosmic puppeteer. Scientists call it the Great Attractor, a gravitational anomaly so powerful it's dragging entire galaxies toward it at speeds of over 1 million miles per hour. But here's the catch: we can't actually see what's causing it. Imagine trying to solve a mystery while someone holds a flashlight directly in your eyes. That's the challenge astronomers face, because our galaxy's dense core blocks our view, leaving this enigma shrouded in darkness. The story begins in the 1970s when astronomers first noticed something odd. Galaxies in our local supercluster, including our own, weren't just drifting randomly. They were all streaming toward the same distant point in the constellation Centaurus. At first, researchers thought it might be a massive cluster of galaxies, but when they peered in that direction, they found far fewer galaxies than needed to explain the gravitational pull. The numbers just didn't add up. It was like standing on a beach feeling a powerful undertow, but looking out to see only calm, shallow water. So what's really out there? One leading theory suggests the Great Attractor might be an enormous concentration of dark matter, that elusive substance that makes up most of the universe's mass but refuses to interact with light. Picture an invisible mountain in space, warping the fabric of reality around it. Others speculate it could be a supercluster we've yet to fully map, a sprawling web of galaxies and dark matter so vast, its gravity reaches across hundreds of millions of light years. But the wildest possibility, some scientists think it might not be a single object at all, but rather a rare cosmic flaw, a kink in the structure of spacetime itself, a remnant from the universe's birth. Imagine the fabric of reality creased like a crumpled sheet, creating a gravitational well that draws everything toward it. Whatever the truth, the Great Attractor reminds us just how much of the universe remains hidden, lurking just beyond our sight. And as powerful telescopes begin to peer through the Milky Way's dust, we might finally catch a glimpse of the force bending the cosmos to its will. Now picture this, a burst of energy so powerful, it outshines entire galaxies, but only for a fraction of a second. These are fast radio bursts, or FRB, some of the most explosive and mysterious signals in the universe. They arrive without warning, flashing across the cosmos like cosmic Morse code, then vanish just as quickly, leaving astronomers scrambling to decode their origins. What makes FRBs so baffling? First, their sheer intensity. In just a few milliseconds, a single burst can release as much energy as the sun does in 80 years. That's like a firecracker outshining a nuclear explosion. Second, their unpredictability. Some FRBs are one-hit wonders, appearing once and never repeating. Others, like the famous FRB 12102, fire off signals in chaotic patterns, teasing scientists with sporadic bursts that defy prediction. And then there's the distance. These signals travel billions of light years, stretching from galaxies so far away. Their light is barely a whisper by the time it reaches us. So where do they come from? The leading suspect is magnetars, ultra-dense neutron stars with magnetic fields so strong they could strip the electrons from your atoms from 1,000 miles away. Imagine a spinning, hypercharged stellar corpse, its crust cracking under immense pressure, releasing violent flares of energy. That might explain some FRBs. But not all of them. Some bursts are too energetic, too structured, or repeat too precisely to fit the magnetar model. This has led to more speculative theories. Could they be the byproduct of advanced alien technology? A civilization harnessing unimaginable power to propel ships or send signals across the void? It's a tantalizing idea, but most scientists lean toward natural, albeit extreme, cosmic phenomena. One wild possibility involves cosmic strings, hypothetical defects in space-time left over from the Big Bang, vibrating like snapped guitar strings and rippling the fabric of reality with bursts of energy. Yet for all the theories, FRBs remain a cosmic riddle. Each new detection peels back another layer of mystery, revealing how little we truly understand about the universe's most violent, fleeting moments. And with every unexplained burst, one thing becomes clearer. The cosmos is far stranger and far more dynamic than we ever imagined. Imagine holding a map where a quarter of the landmarks were invisible, written in ink only certain eyes could see. That's the frustration astronomers face with dark matter, the universe's most pervasive ghost. It's everywhere, bending light and twisting the paths of galaxies, yet it refuses to show itself. We know it exists because the cosmos literally doesn't add up without it. Stars orbit galaxies too fast. Clusters of galaxies move in ways that defy visible mass. Even the blueprint of the early universe, etched into the cosmic microwave background, screams that something invisible is holding everything together. Take spiral galaxies, for example. According to Newton's laws, stars on the outer edges should move slower than those near the center, like planets in our solar system. But when astronomers clock their speeds, they're all whizzing around at roughly the same rate, as if an unseen hand glued them in place, this cosmic glue. Dark matter, it forms vast, diffuse halos around galaxies, a shadowy scaffold that keeps them from flying apart. Without it, our Milky Way would have unraveled billions of years ago. Yet for all its gravitational muscle, dark matter is absurdly shy. Decades of experiments, ultra-sensitive detectors buried deep underground, telescopes scanning for faint X-ray whispers have turned up empty. The leading suspects, WIMP, weakly interacting massive particles, should have shown themselves by now. These hypothetical heavy particles barely interact with normal matter, passing through you right now like you're made of air. But after countless searches, no definitive signal. The alternative, actions, theoretical ultra-light particles that might behave more like waves than particles. Picture the universe filled with an invisible, treacle-thick sea of these ripples, tugging on stars and galaxies. Then there's the radical idea that we've got gravity all wrong. Modified Newtonian dynamics, or MUND, suggests tweaking the laws of physics at cosmic scales instead of invoking invisible matter. But Mund struggles to explain phenomena like the bullet cluster, where two colliding galaxy clusters clearly show gravity working where no visible matter exists, a smoking gun for dark matter's reality. And then there's the kicker, the missing satellite problem. Our cosmological models predict thousands of tiny dwarf galaxies orbiting larger ones like fireflies around a lantern. But we've only found a fraction. Either dark matter behaves in ways we don't understand, or these ghostly galaxies are too faint to spot. It's as if the universe left us a jigsaw puzzle with half the pieces deliberately hidden. Every failed detection, every contradictory observation forces us to dig deeper. Whether it's WIMP actions or something even stranger, dark matter isn't just a placeholder, it's a revolution waiting to happen. And when we finally unmask it, we won't just solve a cosmic mystery. We'll rewrite the rules of reality itself. If dark matter is the universe's invisible scaffolding, then dark energy is the mysterious force quietly tearing it all apart. Picture this, the cosmos isn't just expanding, it's accelerating, as if some unseen hand is pressing harder on the gas pedal with every passing moment. That's the enigma of dark energy, a force so dominant, it makes up nearly 70% of the universe's total energy, yet we have no idea what it actually is. The story starts with a bombshell discovery in the late 1990s. Two teams of astronomers were measuring distant supernova, expecting to find the universe's expansion slowing down under gravity's pull. Instead, they saw the opposite. The light from these exploding stars was fainter than it should have been, meaning space itself was stretching faster over time. It was like tossing a ball in the air and watching it shoot away faster instead of falling back. The implications were staggering. Something was overpowering gravity on cosmic scales, pushing galaxies apart at an ever-increasing rate. Enter Einstein's greatest blunder, or so he thought. Decades earlier, his equations had suggested empty space might contain a repulsive force, a cosmological constant, to keep the universe static. When Edwin Hubble proved the universe was expanding, Einstein dismissed it as a mistake. But now, the cosmological constant was back, reincarnated as dark energy. The twist, its measured value is absurdly tiny, 120 orders of magnitude smaller than quantum physics predicts. It's as if the universe dialed this force to an impossibly precise setting, fine-tuned to allow galaxies, stars, and ultimately us to exist. Some theorists argue dark energy might not be constant at all. Quintessence, a dynamic field permeating space, could wax or wane over time, altering the universe's fate. Others propose even wilder ideas, extra dimensions leaking gravity, or vacuum energy fluctuating in hidden realms, but the most unsettling possibility. That we're seeing the limits of Einstein's relativity, a sign that gravity works differently on cosmic scales. Whatever the answer, dark energy is rewriting our cosmic destiny. Billions of years from now, distant galaxies will vanish beyond an invisible horizon, their light too stretched to reach us. The universe will grow cold, lonely, and dark, a fate sealed by this phantom force we're only beginning to glimpse. And with every new observation, one thing becomes clear: the universe isn't just stranger than we imagine. It's stranger than we can imagine. Now consider the opposite of cosmic excess, vast stretches of nothingness so immense they warp our understanding of space itself. The Boötes void and the Eridanus supervoid are two of the universe's most baffling empty spaces, each spanning hundreds of millions of light-years with barely a handful of galaxies inside. Picture a balloon the size of a stadium, with just a few scattered grains of sand floating inside. That's the scale of emptiness we're talking about. These voids aren't just gaps, they're cosmic deserts so barren, they challenge everything we know about how the universe structures itself. The Boötes void, discovered in the 1980s, stretches 330 million light-years across, a staggering emptiness that would take a beam of light longer to cross than the time since dinosaurs roamed Earth. Yet within this colossal void, astronomers have found only 60 or so galaxies, a fraction of what should exist based on standard galaxy distribution models. It's as if someone carved out a sphere of space and forgot to fill it. The Eridanus supervoid, equally perplexing, overlaps with the infamous cold spot in the cosmic microwave background, a patch of the early universe suspiciously colder than its surroundings. Could these voids be connected to that anomaly? Some theories suggest they're not just empty, they might be actively cooling the universe around them. So how did these voids form? One possibility lies in quantum fluctuations from the Big Bang. Tiny ripples in the infant universe's density might have stretched into vast empty bubbles as space expanded. Another idea is even more mind-bending: collisions with parallel universes in the multiverse. Imagine two bubble universes brushing against each other, their interaction sucking matter out like a cosmic vacuum, leaving behind these eerie blank spots. Then there's the integrated Sachs-Wolf effect, where dark energy's push might be draining energy from light passing through these voids, creating the cold spot. But here's the real twist: these voids shouldn't exist in their current form. Simulations of the universe's evolution predict smaller, denser voids, not these sprawling emptinesses. Their existence hints at gaps in our models, perhaps even flaws in how we understand gravity or dark energy's role. Every galaxy we spot inside these voids becomes a clue, a lonely outpost in a frontier we're only beginning to map. And as we stare deeper into these cosmic holes, one question lingers: are they simply accidents of nature, or signs of something far stranger lurking in the fabric of reality? Deep in the constellation Cygnus, one star behaves like nothing else in the cosmos, Cassie 8462852, better known as Tabby's star. While most stars flicker slightly as planets pass in front of them, Tabby's star doesn't just dim, it plummets. At times, its light drops by a staggering 22%, as if something colossal is blocking its glow. These aren't the orderly dips of orbiting planets. They're chaotic, asymmetrical, and utterly unpredictable, leaving astronomers grasping for explanations that range from cosmic dust to, yes, alien engineering. The mystery began in 2015 when citizen scientists flagged the star's odd behavior in data from NASA's Kepler Space Telescope. Unlike the neat, periodic shadows cast by planets, Tabby's star showed erratic dimming, sometimes gradual, sometimes sudden, with no discernible pattern. One notable event lasted nearly a week, with the star's brightness dropping steadily before rebounding. Another saw abrupt, jagged dips resembling a light flickering behind a tumbling swarm of objects. Even stranger, historical data suggests the star's overall brightness has faded by as much as 14% over the past century, a decline virtually unheard of for a middle-aged star like this. So what's casting these cosmic shadows? Early speculation zeroed in on a swarm of comets, thousands of them, pulverized into a vast cloud of debris. But calculations showed this would require an implausible number of comets, far more than any known system could produce. Then came the dust hypothesis, maybe uneven rings of fine particles like the debris around young stars. Yet Tabby's star isn't young, and such dust should glow in infrared light, which we don't see. Other ideas include a colossal planetary collision, leaving behind a sprawling field of fragments, or even a black hole's accretion disk passing between us and the star. But none perfectly fit the data. And then, of course, there's the elephant in the cosmos, the Dyson swarm hypothesis. Proposed by physicist Freeman Dyson in the 1960s, these theoretical megastructures, vast arrays of solar panels built by advanced civilizations to harness a star's energy, would explain the irregular dimming. A partially completed swarm with panels drifting in loose formation could block light unpredictably. It's a tantalizing thought, but scientists caution it's the least likely explanation. After all, extraordinary claims require extraordinary evidence, and so far, radio telescopes have detected no artificial signals from the star's vicinity. Recent observations add more layers to the puzzle. Spectroscopic data reveals the dimming affects some wavelengths more than others, pointing to fine dust as the likely culprit. Yet this dust behaves oddly. It doesn't disperse as expected, and its particles seem too small to explain the deepest dips. Some researchers propose a screen of nanoparticles, perhaps replenished by evaporating planetary material or even the slow dismantling of a moon. Tabby's star remains a cosmic Rorschach test. Every new observation fuels fresh debate, and every failed explanation underscores how little we understand about stellar behavior. Whether it's exotic astrophysics or just an unlikely cosmic coincidence, this star reminds us that the universe loves to defy expectations. And as telescopes continue to monitor its flickering light, one thing's certain: the truth, when it comes, will be stranger than fiction. The universe is unimaginably vast, with billions of galaxies, each containing billions of stars and planets. Statistically, the numbers suggest we shouldn't be alone, so where is everyone? This is the Fermi paradox, the glaring contradiction between the high probability of extraterrestrial life and the eerie silence we encounter when we listen for it. Named after physicist Enrico Fermi, who famously asked, "Where is everybody?" during a casual lunch discussion in 1950, this paradox has haunted scientists for decades. If intelligent civilizations are common, why haven't we found any traces, no signals, no probes, no megastructures? The unsettling answer might lie in what scientists call filters, potential barriers that prevent civilizations from reaching interstellar communication or travel. One terrifying possibility is the Great Filter, a hypothetical stage so difficult to overcome that it wipes out nearly all life before it can expand beyond its home planet. This filter could lie in our past, meaning we've already beaten extraordinary odds to evolve. Maybe the jump from simple life to complex organisms is astronomically rare. Or perhaps it's ahead of us, lurking in humanity's future. Nuclear war, climate collapse, artificial intelligence gone rogue. Any of these could act as a self-destructive hurdle that extinguishes civilizations before they ever make contact. The silence of the cosmos might not be emptiness at all, but a graveyard of civilizations that never made it. Then there's the zoo hypothesis, the idea that advanced extraterrestrials deliberately avoid contact, observing us like specimens in a cosmic wildlife preserve. Think of it as a galactic prime directive interference would disrupt our natural development, so they remain silent, watching from the shadows. This raises another chilling question. What if we're the primitive ones in a universe teeming with older, wiser civilizations who have mastered the art of staying hidden? Some theories suggest that communication itself might be the issue. Alien signals could be so advanced, so far beyond our current technology, that we simply don't recognize them. Imagine ants trying to decipher Wi-Fi. The signals are all around them, but completely incomprehensible. Or consider the possibility that interstellar travel is so impractical, so energy-intensive, that no civilization ever bothers to leave its own system. The distances between stars might be an insurmountable wall, locking each civilization into cosmic isolation. The Fermi paradox isn't just about aliens, it's a mirror reflecting our own fragility. If the universe is silent because civilizations keep vanishing, what does that mean for us? Are we hurtling toward our own filter, or have we somehow slipped past it? And if intelligent life is truly rare, that places an incredible responsibility on humanity. We might not just be passengers on this pale blue dot, we could be the universe's only chance to know itself. Every mysterious signal, every unexplained phenomenon deepens the paradox, and until we find answers, the silence of the cosmos remains the most profound mystery of all. On the night of August 15, 1977, a radio telescope in Ohio picked up a signal so unusual, the astronomer reviewing the data circled it in red ink and scribbled, "Wow." Next to it, a note that would go down in history. For 72 seconds, the Big Ear telescope detected a narrowband radio burst at 1420 MHz, a frequency scientists had pinpointed as ideal for interstellar communication because it's naturally quiet, undisturbed by cosmic background noise. The signal was 30 times stronger than the surrounding static, matched no known celestial object, and vanished as abruptly as it appeared. 4 decades later, it remains the closest thing we've found to a cosmic hello, and nobody knows where it came from. What makes the WOW signal so compelling? First, its precision. Unlike random cosmic static, it was confined to a sliver of the radio spectrum, just 10 kHz wide, the hallmark of an engineered transmission. Second, its intensity. The signal spiked and faded exactly as expected for a distant source passing through the telescope's fixed beam, ruling out earthly interference. And then there's the silence. Despite repeated searches of the same patch of sky near the constellation Sagittarius, it never repeated, not once. It was as if someone flipped a cosmic flashlight on, pointed it at Earth, then shut it off forever. Over the years, skeptics have proposed explanations. Some suggested it might have been a passing comet, but comets don't emit strong narrowband radio waves, and none were in the area at the time. Others blamed secret military transmissions or satellite reflections, but the signal's frequency was banned for terrestrial use to avoid contaminating astronomical data. The most tantalizing theory, a one-time burst from an alien civilization, perhaps a beacon sweeping the galaxy like a lighthouse beam, briefly illuminating Earth before moving on. But here's the twist. Recent analysis suggests the signal's frequency might have been drifting slightly, as if the source was moving relative to Earth. That could point to a natural origin like a pulsar behaving oddly, or something even stranger, a transmitter mounted on a spacecraft speeding through the void. Either way, the WOW signal stands as a cosmic Rorschach test. For believers, it's proof we're not alone. For skeptics, it's a reminder of how much noise fills the universe. And for scientists, it's the one that got away, a mystery etched in red ink, waiting for another 72 seconds of silence to break. On October 19, 2017, astronomers spotted something streaking through our solar system that defied all expectations, a visitor from interstellar space. Named Oumuamua, Hawaiian for scout or messenger, this mysterious object was the first ever detected from beyond our solar system. But what made it truly extraordinary wasn't just its origin, it was the way it behaved. Unlike any asteroid or comet we'd seen before, Oumuamua displayed a bizarre combination of traits that left scientists arguing for years over what it could possibly be. First, its shape. Most asteroids are lumpy or spherical, but Oumuamua was elongated. Some estimates suggested it was up to 10 times longer than it was wide, like a cosmic cigar tumbling end over end. Then there was its motion. As it zoomed past the sun, it didn't just follow gravity's pull, it accelerated as if something were giving it an extra push. Comets often speed up when their ice sublimates into gas, creating a visible tail, but Oumuamua showed no such outgassing. No dust, no vapor, no coma, just silent, unexplained momentum. Theories exploded. Maybe it was a hydrogen iceberg, a chunk of frozen molecular hydrogen slowly evaporating in sunlight, leaving no visible trace. Hydrogen is invisible to most telescopes, which could explain the lack of outgassing evidence. But hydrogen ice is fragile. Could it have survived the journey through interstellar space? Others proposed it might be a nitrogen iceberg, shed from a Pluto-like exoplanet. Yet these explanations struggled to account for the object's brightness variations, which suggested an unusually reflective surface. Then came the most provocative idea: Oumuamua might not be natural at all. A few scientists, including Harvard astrophysicist Avi Loeb, raised the possibility it could be artificial, a discarded light sail from an advanced civilization. Light sails, thin sheets propelled by solar radiation pressure, fit the acceleration profile. The idea wasn't entirely far-fetched. Humanity's own light sail projects, like Breakthrough Starshot, aim to send tiny probes to nearby stars using similar technology. Could Oumuamua be an ancient relic of another civilization's interstellar exploration? The debate raged, with most astronomers favoring natural origins. Some suggested it was a fragment of a shattered planet ejected during a cosmic collision. Others pointed to dust bunnies, porous aggregates of interstellar material, so light and fluffy that sunlight alone could nudge them. But with Oumuamua already speeding out of sight, the truth remains elusive. By the time we spotted it, it was already leaving, a fleeting whisper of the mysteries lurking between the stars. What Oumuamua left behind was more than just a trail of questions. It was proof that interstellar visitors are real and that some of them might defy our understanding entirely. Future telescopes like the Vera Rubin Observatory will scan the skies for more of these cosmic nomads, and when the next one arrives, we'll be watching, ready to decipher its secrets, whether it's a wandering iceberg, a shattered world, or something even stranger, sent from the depths of space to challenge everything we think we know. High above Earth, in the silent darkness of space, something orbits our planet, something conspiracy theorists claim isn't human-made at all. Meet the Black Knight satellite, a so-called alien artifact supposedly watching us for over 13,000 years. The legend paints it as a sleek, shadowy object, an otherworldly probe sent to observe humanity's rise. But peel back the layers and the truth is far stranger than fiction. A tangled web of misidentified debris, Cold War paranoia, and a dash of Nikola Tesla's cosmic musings. The myth took root in the 1950s when newspapers reported that the U.S. Air Force had detected a mysterious, dark satellite orbiting Earth. At the time, neither America nor the Soviet Union had launched anything capable of such an orbit, sparking whispers of extraterrestrial origins. Then came the clincher. In 1960, a strange object was photographed during a Mercury spacecraft mission, appearing as a jagged, irregular shape against the blackness of space. Conspiracy theorists seized on the image, declaring it undeniable proof of the Black Knight. But here's what they missed: that object was almost certainly a thermal blanket lost during the mission, drifting harmlessly until it burned up in the atmosphere. The legend gained even more traction thanks to a series of odd radio signals. In 1899, Nikola Tesla claimed to have intercepted repeating pulses he believed were attempts at interstellar communication. Decades later, amateur radio operators picked up similar echoes, delayed radio signals bouncing back to Earth minutes after transmission. Scientists eventually traced these to a phenomenon called long-delayed echoes, likely caused by charged particles in the ionosphere. But in the conspiracy world, these echoes became the Black Knight's haunting broadcasts, a beacon from an ancient alien observer. So why does the myth endure? Part of its sheer human nature, we're wired to see patterns even where none exist. A tumbling piece of space junk becomes a precision-crafted relic. A routine thermal blanket transforms into evidence of extraterrestrial surveillance. But there's also the allure of the unknown. Space is vast and full of mysteries, and the idea that something or someone might be out there watching taps into our deepest existential curiosities. Modern astronomers have debunked the Black Knight repeatedly. The satellite sightings align with known space debris, like the remnants of old satellites or discarded rocket stages. Radar anomalies once blamed on the Black Knight turned out to be natural ionospheric disturbances. Yet, like all good myths, it refuses to die. Every new blurry photo from the International Space Station reignites the frenzy, proving one thing: in the absence of answers, humanity will always fill the void with stories. And whether it's thermal blankets or Tesla's echoes, the Black Knight remains a testament to our endless fascination with the stars and the shadows that might hide within them. Imagine a cosmic food chain where the largest galaxies don't just drift peacefully through space, they devour their smaller neighbors in a slow-motion feast spanning billions of years. This is galactic cannibalism, a violent yet elegant process that shapes the universe as we know it. At the center of this celestial drama lies a paradox. The very same force that holds galaxies together, gravity, also tears them apart, weaving an intricate dance of creation and destruction on scales almost too vast to comprehend. Take our own galactic backyard. The Milky Way, serene as it appears from Earth, is a predator. Over the past 4 billion years, it's consumed at least a dozen smaller galaxies, tearing them apart with its immense gravitational pull. One of its most famous victims, the Sagittarius dwarf galaxy, once an independent system, it's now little more than a stellar stream, a ribbon of stars stretched into a looping arc around the Milky Way like crumbs scattered from a cosmic meal. Astronomers can trace its remains across the night sky, a ghostly testament to the violence hidden behind the galaxy's sparkling disk. But how does this process actually unfold? Picture a small galaxy venturing too close to a larger one. Dark matter, the invisible scaffold that makes up most of a galaxy's mass, plays the role of cosmic glue. As the smaller galaxy approaches, tidal forces, the difference in gravity between its near and far sides, start to stretch it like taffy. Stars and gas are pulled loose, forming long, luminous tendrils called tidal streams. Over time, these streams disperse, their stars assimilated into the larger galaxy's halo. The core of the devoured galaxy might linger for a while, but eventually it too dissolves, its identity erased by the predator's hunger. Andromeda, our nearest galactic neighbor, is an even more voracious eater. Observations reveal it's littered with the remnants of past mergers, shells, loops, and clusters of stars that don't belong. One study suggests Andromeda's outskirts are dominated by stars from a single massive meal, a galaxy it shredded 8 to 10 billion years ago. The aftermath is so vast, it's rewired Andromeda's entire outer structure. What makes these mergers so critical to understanding the universe? For one, they're the engines of galactic growth. Most large galaxies, including ours, didn't form in isolation. They built themselves by swallowing others. But there's a twist. These collisions aren't the chaotic smash-ups you might expect. Because galaxies are mostly empty space, actual stellar collisions are rare. Instead, it's the gravitational interactions that reshape them, shuffling stars into new orbits and triggering bursts of star formation as gas clouds collide and compress. Dark matter's role here is especially fascinating. Without it, galaxies wouldn't have enough gravity to capture their prey. Simulations show that dark matter halos act like cosmic nets, ensnaring smaller galaxies long enough for their stars to be stripped away. Yet dark matter itself remains aloof. Particles pass through each other without interacting, meaning the halos of merging galaxies simply blend, like two shadows merging into one. The Milky Way's fate is sealed in this cycle of cannibalism. In about 4 billion years, it will collide with Andromeda, creating a new hybrid galaxy astronomers nicknamed Milkdromeda. The process will take billions of years, with both galaxies stretching and warping each other before finally settling into a new shape. Stars will be flung into new orbits, and the night sky from any surviving planets will look utterly alien, a mosaic of two former galaxies now intertwined forever. These mergers aren't just destructive, they're creative. The influx of new gas can reignite dormant star-forming regions, birthing generations of new stars. Some astronomers even speculate that our own solar system exists because of an ancient galactic merger that stirred up the Milky Way's gas, triggering the birth of the Sun. Galactic cannibalism forces us to rethink what a galaxy even is. They're not static islands of stars but dynamic, evolving entities shaped by their violent histories. Every time we map a new stellar stream or spot the faint glow of a devoured dwarf galaxy, we're reading a chapter in this epic story of cosmic consumption, one where the universe builds its grandest structures one meal at a time. In the vast emptiness between the planets, two tiny spacecraft defied expectations in a way that still puzzles scientists decades later. NASA Pioneer 10 and 11, launched in the early 1970s to explore the outer solar system, became famous not just for their missions but for how they drifted off course. As these probes ventured beyond Saturn, tracking data revealed something bizarre. Both were slowing down ever so slightly, as if an invisible hand were tugging them backward toward the Sun. This unexpected deceleration, just a fraction of a nanometer per second squared, became known as the Pioneer anomaly, a cosmic mystery that would linger for over 30 years. At first, scientists suspected instrument error. Maybe the probe's aging systems were generating false signals, but the data held firm. The Pioneers weren't just off trajectory, they were experiencing a constant, unaccounted-for deceleration that grew more pronounced as they neared the edge of the solar system. The effect was subtle, equivalent to the gravitational pull of a speck of dust millions of miles away, yet it persisted year after year. Researchers scrambled to explain it. Could it be drag from lingering interplanetary gas? The gravitational pull of undiscovered Kuiper belt objects? Even the influence of dark matter was floated, though calculations showed the required density was impossibly high. Then came the leading theory of thermal recoil. The Pioneers, powered by radioactive plutonium, generated heat that radiated unevenly from their dish-shaped antennae. This asymmetrical emission, scientists argued, might have created a tiny but constant thrust in the opposite direction, like a car slowing down because someone opened the trunk and let hot air push against it. By 2012, meticulous reconstructions of the probe's heat distribution seemed to confirm this, with models matching the observed deceleration almost perfectly. Case closed, not quite. While thermal radiation explains most of the anomaly, lingering discrepancies remain. Some measurements still don't align perfectly with the models, hinting that another force, perhaps something more fundamental, might still be at play. Could there be flaws in our understanding of gravity itself? Modified theories like modified Newtonian dynamics (MUND), which tweak gravity's behavior at extreme scales, gain traction as potential explanations. Others speculate about the influence of the solar system's local dark matter distribution, though no direct evidence supports this. The Pioneer anomaly's legacy endures because it exposes how even our most precise instruments can uncover gaps in physics. Those minuscule deviations, barely perceptible over decades, remind us that space isn't just empty, it's a testing ground for the laws we think we've mastered. And as new missions venture farther into the void, they carry the lessons of the Pioneers, that sometimes the universe's quietest whispers hold its loudest challenges. The cosmic microwave background, the faint afterglow of the Big Bang, should be the most impartial observer in the universe. A relic from a time before galaxies, stars, or even atoms, it ought to reveal a cosmos perfectly uniform, its imperfections randomized in every direction. Yet when scientists mapped its subtle temperature variations, they stumbled upon something that defied reason, a pattern eerily aligned with the plane of our solar system. This bizarre correlation, dubbed the axis of evil, isn't just a curiosity, it's a potential crack in the foundation of modern cosmology, a hint that either our measurements are fatally flawed or the universe isn't playing by the rules we thought we knew. The story begins with NASA Wilkinson Microwave Anisotropy Probe, or WMAP, launched in 2001 to study the CMB in unprecedented detail. The data it returned was exquisite, revealing temperature fluctuations as tiny as 1 part in 100,000, the seeds of all cosmic structure. But hidden in that data was an anomaly no one expected. The CMB's fluctuations weren't entirely random. Instead, they showed a curious preference, aligning roughly with the ecliptic, the plane in which Earth and the other planets orbit the Sun. Later measurements by the Planck satellite confirmed the alignment, deepening the mystery. It was as if the universe's oldest light somehow knew about our solar system's orientation, a cosmic coincidence so improbable it bordered on absurd. Skeptics rushed to dismiss it. Maybe it was an artifact of instrument calibration or foreground interference from dust in the Milky Way. Others argued it was just statistical noise, a fluke that would vanish with better data. But the more researchers looked, the harder the anomaly became to ignore. The alignment wasn't just with the ecliptic, it also correlated with the equinoxes, the points where the sun crosses the celestial equator. The odds of this happening by chance, less than 1 in 10,000. This isn't just a quirky observation, it strikes at cosmology's core principles. The CMB should be isotropic, meaning its properties shouldn't depend on the observer's location or orientation. If the axis of evil is real, it implies a preferred direction in the universe, a cosmic north that breaks the symmetry we've always assumed. Some theories take this even further, suggesting it could be evidence of a pre-Big Bang structure, a fingerprint from an earlier epoch imprinting itself on our universe's birth. Others propose wilder ideas, like our universe being one bubble in a vast multiverse, its walls subtly warping the CMB, but the most unsettling possibility. That we're seeing the limits of our own perception. Like a fish unaware of the water it swims in, could some fundamental aspect of our solar system's environment, something we've yet to even conceptualize, be distorting our view of the cosmos? Until we know for sure, the axis of evil remains a thorn in cosmology's side, a quiet rebellion against our most cherished assumptions. And whether it's a measurement quirk or a cosmic revolution in waiting, one thing's certain: the universe still has secrets it's not ready to surrender. Beyond the orbit of Neptune, the solar system doesn't just fade quietly into darkness, it ends with a cosmic cliffhanger. Astronomers call it the Kuiper Cliff, a boundary roughly 50 astronomical units from the Sun where the number of icy Kuiper belt objects suddenly plummets. It's as if someone drew a line in the cosmic sand and declared, "No further." This abrupt drop defies expectations, leaving scientists scrambling for explanations that range from hidden planets to the ghosts of ancient planetary migrations. The Kuiper Belt, a sprawling ring of frozen debris left over from the solar system's formation, should theoretically extend much farther. Models predict a gradual tapering of objects like a beach sloping gently into the ocean. Instead, observations reveal a sharp cutoff, like stepping off the edge of an underwater trench. The most famous resident of this region, Pluto, orbits safely within this boundary. But venture beyond and the belt's population crashes. Only a handful of objects have been spotted past 50O, and those that do exist are eerily clustered, as if something herded them there. So what's carving this cosmic cliff? One tantalizing theory points to an unseen planet, something massive enough to sweep the outer belt clean. This fits neatly into the ongoing hunt for Planet 9, a hypothetical world 10 times Earth's mass that could explain several solar system oddities. If such a planet exists, its gravity might have shepherded objects inward, leaving the outer Kuiper belt barren. Imagine a snowplow pushing debris to the side of a road, only on a planetary scale over billions of years. But not all researchers are convinced. Another camp argues the cliff could be a scar from the solar system's violent youth. During the era of planetary migration, Neptune's orbit is thought to have shifted outward, scattering icy bodies like a gravitational bulldozer. Some simulations show this migration could have ejected most objects beyond 50O, leaving behind only the stragglers we see today. The Kuiper Cliff, in this view, is a fossilized border marking where Neptune's influence waned. Then there's the simplest explanation: we just haven't looked hard enough. The outer Kuiper belt is a twilight zone where sunlight is so faint, objects are nearly invisible to our telescopes. What appears to be a dramatic drop-off might just be an observational blind spot. New surveys, like the Vera Rubin Observatory's upcoming scans, could fill in the gaps or deepen the mystery by confirming the cliff is real. The stakes here are higher than just solving a celestial puzzle. If Planet 9 is responsible, its discovery would rewrite our solar system's history. If it's migration scars, we're glimpsing the aftermath of a planetary dance billions of years in the making. And if it's an illusion of limited data, well, that's a humbling reminder of how much we still don't know about our own cosmic backyard. One thing's certain, beyond Neptune, the solar system still has secrets to spill, and the Kuiper Cliff is just the beginning. Amid the swirling chaos of most nebulae, where gas and dust twist into unpredictable shapes, one cosmic structure stands out like a meticulously crafted jewel: the Red Rectangle Nebula. This enigmatic cloud, glowing crimson against the blackness of space, defies all expectations with its near-perfect geometric symmetry. From our vantage point, it appears as an eerily precise rectangle, crossed by diagonal beams of light that form an unmistakable X at its core. No other nebula in the known universe looks quite like this, a structure so orderly it seems almost artificial. Yet the truth behind its formation is even more fascinating than science fiction. The Red Rectangle's secret lies in the dance of two aging stars at its heart. These binary stars, locked in a tight orbital embrace, are the architects of its bizarre shape. As one star sheds its outer layers in the final stages of stellar evolution, the other star's gravity sculpts that ejected material into a pair of cone-shaped outflows. We're seeing those cones almost edge on, their sides appearing as the rectangle's borders, while their intersecting tips create the glowing X. Imagine two ice cream cones placed tip to tip and spun, their rims tracing the red rectangle's sharp edges. But here's where the mystery deepens. While other binary systems create nebulae, none exhibit this level of symmetry or the red rectangle's uncanny chemical cocktail. Spectroscopy reveals a treasure trove of complex organic molecules, including polycyclic aromatic hydrocarbons, building blocks for compounds found in everything from soot to DNA. How did these molecules form in such abundance here? One theory suggests the central stars, cooler and richer in carbon than most, are acting as cosmic chemists, forging these compounds in their stellar winds. Another idea points to shockwaves from the star's interactions, crushing simple molecules into more complex structures like a celestial pressure cooker. Then there's the color, a deep, unnatural red that gives the nebula its name. Most nebulae glow in blues or greens from ionized gases, but the red rectangle's hue comes from those very organic molecules scattering starlight. It's as if the cosmos took a jar of rubies and vaporized them across light years of space. Even more intriguing, this same red glow has been detected in the interstellar medium, hinting that the processes at work here might be seeding the galaxy with the ingredients for life. The red rectangle challenges our assumptions about how stars die and what they leave behind. Most planetary nebulae, the remnants of sun-like stars, are messy, asymmetrical affairs. This one's precision suggests forces we're only beginning to understand, a cosmic interplay of gravity, chemistry, and time that turns stellar death into artistry. And as the central stars continue their slow-motion waltz, they're writing their final chapter not in chaos, but in geometry, a farewell note etched in organic molecules and light, waiting for us to decode its secrets. Stretching across an almost unimaginable 10 billion light-years, the Hercules Corona Borealis Great Wall isn't just a structure, it's a cosmic paradox. This titanic filament of galaxies, the largest known arrangement of matter in the observable universe, is so vast that its very existence teeters on the edge of impossibility. Picture a river of galaxies so wide, light would take twice the age of Earth just to traverse one end of it, and yet, according to our deepest cosmological principles, something this colossal shouldn't exist at all. The trouble starts with the cosmological principle, a cornerstone of modern astronomy asserting that, on large enough scales, the universe should look roughly the same everywhere. No preferred locations, no grand structures, just a uniform cosmic soup. But the Great Wall defies this. Discovered in 2013 by mapping gamma-ray bursts, the death cries of massive stars, this behemoth isn't just a cluster of galaxies. It's a woven tapestry of superclusters, a spiderweb of matter threading through the constellations Hercules and Corona Borealis, binding together hundreds of thousands of galaxies in a gravitational embrace. Its scale is staggering. If you shrank the observable universe to the size of a football field, the Great Wall would still stretch from one 10-yard line to the other. Critics argue it might be a trick of perspective, a chance alignment of unrelated structures viewed from just the right angle, but the statistical odds of that are astronomically low. Simulations of the universe's large-scale structure rarely produce anything approaching this magnitude. It's like rolling a die 1,000,000 times and never once landing on 6, then suddenly getting 100 sixes in a row. The Great Wall seems to whisper that either our models are incomplete or the universe played a cosmic joke on us. One radical explanation: the Great Wall could be a relic of the universe's infancy, a fossilized ripple from the Big Bang itself. In the chaotic moments after creation, quantum fluctuations might have seeded regions of slightly higher density, which then grew into these unimaginably vast structures. Alternatively, some theorists propose an even wilder idea, that the wall is evidence of a collision between bubble universes in the multiverse, their boundaries imprinting scars on the fabric of reality. But the most unsettling possibility is that we're seeing the limits of our own observations. The Great Wall lies near the edge of the observable universe, where distortions from cosmic expansion could be magnifying its apparent size. Yet, even accounting for this, its scale strains plausibility. Whether it's a flaw in our theories, a glimpse of deeper physics, or simply the universe reminding us how small our maps still are, the Hercules Corona Borealis Great Wall stands as a silent challenge, a monument to all we don't yet understand. And until we crack its code, it remains a beautiful, confounding monument to the cosmos' refusal to fit neatly into our equations. Imagine a world where the ground beneath your feet isn't rock, it's diamond. Not scattered gemstones, but an entire planet so rich in carbon, its core could be one colossal cosmic jewel. Welcome to 55 Cancri E, a scorching super-Earth orbiting so close to its star that a single year lasts just 18 hours. This hellish world, twice Earth's size but nearly 9 times its mass, shouldn't exist under normal planetary formation rules. Yet here it is, defying expectations with a composition so exotic, it's forced astronomers to rethink how planets are born. What makes this planet so special? It's all about carbon. Most rocky worlds, like Earth, form from material rich in oxygen and silicon, think sand and stone. But 55 Cancri E seems to have formed in a region stuffed with carbon, the same element that makes up diamonds and graphite. Under extreme pressure and heat, carbon crystallizes into diamond, leading scientists to speculate this planet's interior could be a seething mass of compressed carbon, with layers of diamond dozens or even hundreds of miles thick. Picture an Earth-sized gemstone glowing red-hot under the relentless glare of its nearby star. But here's the twist: this isn't just a diamond wrapped in a planetary bow. The surface conditions are brutal enough to melt any prospector's dreams. Temperatures soar above 4,000 degrees Fahrenheit, hot enough to vaporize metals. The atmosphere, if it exists at all, might be a haze of carbon monoxide or hydrogen cyanide, poisonous even by cosmic standards, and that diamond core. It's likely buried beneath oceans of superheated graphite, a sludgy cousin of the carbon we know from pencil leads. Theories suggest this world is part of a rare class called carbon planets, celestial oddities that form around stars with unusually high carbon-to-oxygen ratios. Unlike Earth, which owes its mineral diversity to oxygen-rich chemistry, carbon planets are forged in environments where carbon dominates, giving birth to landscapes we can barely imagine. Silicon carbide might replace quartz, molten iron carbide could flow like lava, and deep below, the crushing pressures transform carbon into crystalline structures far grander than any diamond ever mined on Earth. Yet 55 Cancri isn't just a scientific curiosity, it's a window into the universe's wild diversity. If planets like this exist, what else lurks in the cosmos? Worlds crusted in sapphire, oceans of liquid hydrocarbons, the discovery challenges our assumptions about what's possible, proving that the universe's recipe book for planets is far more inventive than we ever guessed. And while we'll never set foot on this glittering inferno, its very existence sparkles with questions waiting to be unearthed. Stephen Hawking's most famous paradox didn't just challenge physics, it threatened to unravel reality itself. The black hole information paradox begins with a simple question. When matter gets swallowed by a black hole, does it disappear forever? According to Einstein, yes. The intense gravity crushes everything into a singularity, a point of infinite density where the very concept of information, the quantum states that make up particles, gets erased. But here's the catch: quantum mechanics insists information can never be destroyed. It might get scrambled, but it must persist. So which is it? Does the universe play by quantum rules, or does gravity get to break them inside black holes? This contradiction isn't just academic. If information truly vanishes, it means quantum theory, the foundation of everything from chemistry to computers, is fundamentally flawed. Hawking's initial solution made the problem worse. He calculated that black holes emit radiation, now called Hawking radiation, slowly evaporating over time. But crucially, this radiation appeared random, carrying no trace of the original swallowed matter. The information seemed lost for good, violating quantum determinism. Physicists split into warring camps. Some argued the information must leak out somehow, encoded in subtle correlations within the radiation. Others proposed radical ideas like the firewall paradox, suggesting an invisible wall of searing energy at the black hole's edge that vaporizes incoming matter, preserving information but defying relativity's prediction of a smooth, uneventful fall. Then came the holographic principle, a game-changing notion that reimagines reality itself. Maybe the information isn't lost because it was never inside the black hole to begin with. Instead, it gets smeared across the event horizon like a cosmic hologram, a two-dimensional surface encoding everything that falls in. Think of it like burning a book. The pages are gone, but if the smoke carries every word in its swirling patterns, the information still exists. Recent breakthroughs in string theory and quantum gravity suggest this might be the answer. In 2019, researchers calculated that Hawking radiation could indeed carry hidden information after all, entangled with the black hole's interior in ways we're only starting to decode. The paradox isn't fully solved, but the pieces are falling into place, pointing toward a universe where even the most destructive forces play by quantum rules. And if they're right, black holes aren't cosmic shredders, they're the universe's most sophisticated storage devices, holding onto every secret they swallow. Saturn isn't just the solar system's ringed beauty, it's also home to one of the most perplexing atmospheric puzzles ever observed. Hovering over its north pole is a hexagon. Not a rough approximation, not a fleeting pattern, but a near-perfect geometric shape spanning 25,000 kilometers, wide enough to fit 4 Earths side by side. This colossal six-sided storm has persisted for decades, possibly centuries, defying every expectation of how planetary weather should behave. On Earth, storms rage in spirals or loose clusters, shaped by the chaos of wind and temperature. But Saturn's hexagon is so precise, it looks as though it was etched into the planet's atmosphere by some celestial draftsman. The secret lies in the planet's jet streams, rivers of wind roaring at speeds over 300 miles per hour. Unlike Earth's meandering jet streams, Saturn's northern polar jet forms a razor-sharp boundary, trapping turbulence within its walls. Picture water swirling around a drain, but instead of a smooth circle, the flow locks into a rigid hexagon. Laboratory experiments with spinning fluids have recreated similar shapes, suggesting the hexagon arises from deep atmospheric dynamics. When fluids of different densities rotate at high speeds, stable polygonal patterns can emerge, like cosmic physics doodling in the sky. Yet this doesn't fully explain why Saturn's hexagon is so unnervingly precise. Earth storms, even the most powerful hurricanes, dissolve into asymmetry, shredded by landmasses and temperature variations. Saturn, a gas giant with no surface to disrupt the flow, allows these geometric currents to stabilize, but there's another twist: the hexagon isn't static. Its clouds churn violently, with smaller vortices dancing along its edges like celestial fireflies. Infrared imaging reveals the storm plunges hundreds of kilometers into Saturn's atmosphere, a towering structure anchored by forces we've yet to fully map. Some theorists propose the hexagon might be a standing wave, a vibration frozen in the atmosphere like a note held on a cosmic guitar string. Others speculate it's linked to Saturn's internal rotation, a fingerprint of deeper, unseen layers where magnetic fields and fluid dynamics collide. Then there's the wild card: the hexagon's eerie similarity to quantum fluid experiments, where supercooled particles form geometric shapes under extreme conditions. Could Saturn's atmosphere be echoing phenomena usually confined to the subatomic world? One thing's certain: this isn't just a weather pattern. It's a laboratory for physics at scales we can barely imagine, where the rules of fluid dynamics twist into something alien and beautiful. And as Saturn's seasons slowly shift, each lasting over 7 Earth years, the hexagon watches on, a silent sentinel guarding secrets we're only beginning to decipher. In a universe where galaxies swirl in elegant spirals or clump into messy blobs, Hoag's object stands apart, a perfect cosmic bullseye floating against the void. Discovered in 1950 by astronomer Arthur Hoag, this ring galaxy is so symmetrical it looks almost manufactured. At its center sits a dense yellow core of aging stars, surrounded by a pristine blue ring of younger, hotter stars separated by a gap so clean it might have been drawn with celestial compasses. The strangest part: no one knows how it formed. Most ring galaxies emerge from violent collisions where one galaxy punches through another, sending ripples of stars outward like stones dropped in water. But Hoag's object shows no signs of a recent impact. No debris, no twisted trails, just an eerie, undisturbed perfection that defies every textbook explanation. Some theories suggest it's the remnants of an ancient, unstable disk that fragmented over billions of years, its outer stars migrating outward while the core collapsed inward. Others propose a slower, gentler process, an accretion of gas from intergalactic space, igniting new stars in a precise circle around the older core. Then there's the wild card: gravitational instabilities from a long-ago encounter with a now-vanished neighbor, leaving behind this structural echo. Whatever the truth, Hoag's object is a cosmic whisper of how much we still don't understand about galactic evolution. Now shift your gaze to a different kind of ring, one not of birth but of death. The Southern Ring Nebula, a glowing halo of gas 2,000 light-years away, is the final masterpiece of a dying star. Unlike Hoag's crisp symmetry, this nebula's beauty is chaotic, its petals of ionized gas expanding outward like a stellar inkblot test. At its heart, a white dwarf, the burned-out core of what was once a sun-like star, pumps ultraviolet radiation into its own funeral shroud, lighting up the expelled layers of its former atmosphere. The result isn't just a ring, it's a layered sculpture with tendrils and bubbles revealing the star's death throes in exquisite detail. What makes these two structures so mesmerizing is how they challenge our definitions. Hoag's object defies the chaos of galactic collisions, offering pristine order where we expect wreckage. The Southern Ring Nebula turns stellar death into artistry, proving even destruction can create breathtaking patterns. One is a galaxy that shouldn't exist, the other is a corpse that refuses to fade quietly. Together, they remind us that the universe isn't just a collection of rules, It's a canvas where physics and chance conspire to paint the unimaginable. The TRAPPIST-1 system should be buzzing with activity. At least, that's what we expected. 7 Earth-sized planets, 3 nestled snugly in the star's habitable zone, where temperatures could allow liquid water to exist. A cosmic jackpot for alien hunters. Yet when we point our radio telescopes toward this red dwarf star 39 light-years away, we're met with silence, not just quiet, but an eerie, unnatural hush. No signals, no whispers of technology, no cosmic hello. Just 7 rocky worlds spinning in perfect, undisturbed solitude. What makes this absence so unsettling isn't just the lack of contact, it's the growing realization that even the most promising alien real estate might be empty after all. Let's start with the star itself. TRAPPIST-1 is an ultra-cool dwarf, a smoldering ember compared to our Sun. Its faint glow bathes its planets in perpetual twilight, but this dimness comes at a cost. Red dwarfs are notoriously tempestuous, prone to violent flares that can strip atmospheres and blast surfaces with lethal radiation. Any life here would need to endure conditions far harsher than Earth's worst extremes. Then there's tidal locking, a gravitational quirk forcing these planets to always show the same face to their star, like the Moon does with Earth. Imagine a world where one side bakes in eternal daylight, the other shrouded in endless night, with only a thin, twilit sliver where temperatures might be tolerable. Could life thrive in such a fractured environment? The deeper mystery lies in the radio silence. SETI, the search for extraterrestrial intelligence, has scanned TRAPPIST-1 repeatedly, listening for the faintest hints of artificial signals. Nothing, not even the unintentional radio leakage that spills from Earth, the byproduct of our broadcasts and radar. This absence forces us to confront an uncomfortable truth. Habitable doesn't mean inhabited. A planet might tick every box for liquid water and stable temperatures, yet still be barren, a cosmic desert masquerading as an oasis. Some scientists argue we're looking for the wrong signs. Maybe life around red dwarfs evolved to communicate with lasers or neutrinos, skipping radio entirely. Others suggest these worlds could be oceanic, their surfaces devoid of land and without continents. The tectonic activity driving Earth's carbon cycle might stall, stifling complex life. The most haunting possibility, that life here never made it past the microbial stage, snuffed out by flares or frozen in the tidal lock's unforgiving grip. The TRAPPIST-1 system isn't just a lesson in astronomy, it's a mirror. Each silent planet reflects our own assumptions about what makes a world alive. We built our hopes on Earth-like conditions, but the universe might have other plans. And as we keep listening, the quiet grows louder, a reminder that even in a galaxy teeming with planets, true neighbors might be rarer than we ever imagined. Picture a black hole not as a lurking predator at a galaxy's core, but as a cosmic fugitive tearing through space at unimaginable speeds. That's exactly what the Hubble Space Telescope witnessed when it spotted a supermassive black hole, weighing as much as 20 million suns, barreling away from its home galaxy. Behind it stretched something even more bizarre, a contrail of newborn stars glowing like breadcrumbs left in the void. This wasn't just a black hole on the move, it was rewriting the rules of how these cosmic monsters interact with their surroundings. What could fling a black hole with enough force to escape its galaxy? The answer lies in the violent dance of black hole mergers. When two supermassive black holes spiral toward each other, their collision sends ripples through space-time called gravitational waves. If these waves aren't emitted symmetrically, the resulting kickback can launch the newly merged black hole at speeds exceeding 1,000 kilometers per second, fast enough to break free from its galaxy's gravitational grip. It's like firing a cannon in zero gravity. The recoil sends the shooter flying backward. In this case, the cannon is the unfathomable energy of colliding singularities, and the shooter is a black hole now doomed to wander the cosmos alone. But the real magic lies in that glowing stellar trail. As the black hole plows through intergalactic gas, it compresses and shocks the material in its wake, triggering star formation in a process normally seen in dense nebulas. The result, a narrow 55,000 light-year long river of young blue stars, tracing the black hole's path like a cosmic jet stream. This phenomenon turns conventional wisdom on its head. Black holes aren't just destroyers of worlds, but accidental creators, sculpting new stellar landscapes as they flee. The discovery raises a tantalizing question. How many more of these rogue black holes are out there, invisible because they've left no trail? Current estimates suggest thousands could be drifting undetected between galaxies, their presence revealed only by subtle lensing effects or the rare instances where they collide with gas clouds. Some might even be primordial black holes formed in the Big Bang's first moments, lurking in the darkness since before galaxies even existed. Yet the implications go deeper. If recoiling black holes are common, they could explain why some galaxies lack central black holes altogether. Their engines were violently ejected long ago. Others might carry stripped galactic cores along for the ride, tiny satellites orbiting the runaway behemoth. And in the distant future, when galaxies merge into a single supergalaxy, these nomads could become the last free black holes in the universe, untethered and alone in the cooling cosmos. The runaway black hole isn't just an oddity, it's a glimpse into the chaotic, high-stakes physics governing the universe's most extreme objects. And as telescopes grow sharper, we may find these cosmic outlaws are far more than rare exceptions. They could be silent witnesses to the violent mergers that shape the galaxies we see today. The universe had barely blinked into existence when these cosmic titans appeared, galaxies so massive, so mature they shouldn't exist. That's the bombshell dropped by the James Webb Space Telescope, spotting colossal galaxies thriving just 300 million years after the Big Bang. These weren't the faint, infant flickers astronomers expected. They were fully formed behemoths brimming with stars that by all rights should have taken billions of years to assemble. It's like finding a skyscraper in the ruins of an ancient civilization, something that advanced simply couldn't have been built that quickly. At the heart of the mystery lies a simple question: how? Current cosmological models paint the early universe as a slow-cooked cosmic stew, where tiny fluctuations in density gradually coalesced into stars, then galaxies over eons. Yet JWST images reveal sprawling galactic disks and bulging cores, some with as many stars as our Milky Way, but existing when the universe was less than 2% of its current age. The numbers don't add up. For structures this vast to form so soon, either our understanding of galaxy formation is fundamentally flawed, or the universe got a head start we never accounted for. One radical theory points to primordial black holes, hypothetical monsters born not from dying stars, but from the violent density fluctuations of the Big Bang itself. These ancient black holes could have acted as cosmic seeds, their immense gravity pulling in surrounding matter at breakneck speeds, jump-starting galaxy growth long before normal processes could take hold. Imagine planting a redwood sapling only to return the next day and find it's already taller than a sequoia. Primordial black holes might have been the unnatural fertilizer that let galaxies grow impossibly fast. Then there's the unsettling possibility that dark matter, the invisible glue holding galaxies together, behaved differently in the early universe. Maybe it clustered more tightly, creating denser gravitational wells for gas to collapse into. Or perhaps the very laws of physics weren't as constant as we think. Some theorists suggest temporary shifts in gravity's strength or the fine structure constant could have turbocharged star formation, though these ideas remain speculative at best. The most disruptive explanation: our cosmic timeline is off. What if the Big Bang wasn't the true beginning but a reboot, a phase transition in a much older universe? Cyclic cosmology models propose endless cycles of expansion and contraction, with each bang inheriting structures from the previous iteration. Those impossible galaxies might not be young at all, but cosmic survivors from a prior epoch, their light stretched and redshifted to mimic youth. JWST findings have thrown cosmology into beautiful chaos. Every solution on the table demands rewriting some chapter of our cosmic story, whether it's galaxy formation, dark matter, or the Big Bang itself. And as the telescope peers even deeper into the past, one thing's certain: the early universe was far stranger, far more inventive than we ever dared to dream. The Moon today is a silent, airless world, its surface scarred by billions of years of meteor impacts, but hidden in its ancient rocks lies evidence of a dramatic past. Samples brought back by Apollo astronauts contain something astonishing: minerals magnetized as if they'd formed in the presence of a strong magnetic field. This shouldn't be possible. Unlike Earth, with its churning molten iron core generating our protective magnetic shield, the Moon's core is too small and inert to power such a dynamo. So how did our closest neighbor once boast a magnetic field nearly as strong as Earth's, only to lose it completely? One theory points to a cosmic collision so violent, it jump-started the Moon's magnetism in its infancy. In the Moon's chaotic early years, debris from giant impacts may have swirled around it in a temporary disk, creating electrical currents as it interacted with the young Moon's residual heat. Picture a blender full of molten rock spinning at impossible speeds. This chaotic motion could have acted like a dynamo, generating a short-lived magnetic surge before fizzling out. Supporting this, some lunar rocks dating back 4 billion years show the strongest magnetization, as if the Moon's magnetic field peaked during its most brutal bombardment phase. But there's another twist. Recent simulations suggest the Moon's mantle itself might have been the engine. Early in its history, the lunar interior was hot enough to churn with convection currents, much like Earth's mantle today. If dense, mineral-rich material sank while lighter material rose, this movement, coupled with the Moon's rapid rotation, could have created a dynamo effect without a traditional iron core. Think of it like stirring honey into tea. The swirling motion generates tiny currents, just on a planetary scale. This mantle dynamo would have been fragile, collapsing as the Moon cooled and its interior settled into stillness. The implications stretch far beyond our lunar companion. If small, coreless worlds can generate magnetic fields through alternative mechanisms, it raises thrilling possibilities for exomoons orbiting distant gas giants. A magnetic field shields a world from lethal solar radiation, preserving atmospheres and potentially creating safe havens for life. Imagine icy moons in other star systems, their subsurface oceans protected not by metallic cores, but by the turbulent movements of their own rocky mantles or the gravitational tides of their host planets. Yet the Moon's magnetic history remains a puzzle missing critical pieces. Some rocks show signs of magnetization from just 1 billion years ago, long after the Moon's interior should have gone quiet. Could residual pockets of molten material have lingered, or did external forces like Earth's magnetic field temporarily induce magnetism in the lunar crust? Each returned sample adds new clues, but the full story may require digging deeper, literally. Future missions drilling into the Moon's polar regions or its far side could uncover minerals that rewrite our understanding of lunar geology. What's certain is this: the Moon was never the static, unchanging orb we once thought. Its past was dynamic, almost alive with magnetic storms and geological upheavals. And as we piece together its lost field, we're not just solving a lunar mystery, we're learning how even the smallest worlds can harbor cosmic surprises. We know the universe is built on an intricate scaffolding, the cosmic web, a vast network of galaxies and gas stretching across billions of light years. But here's the puzzle: when astronomers tally up all the normal matter, the stuff that makes up stars, planets, and us, they find half of it is missing. Not dark matter, not some exotic particle, but ordinary atoms, the building blocks of everything visible. This is the case of the missing baryons, one of cosmology's most persistent mysteries. So where did these atoms go? The leading suspect is something called the warm-hot intergalactic medium, or WIM, an elusive web of diffuse gas hiding in the spaces between galaxies. Picture steam rising from a cosmic cup of tea, so thin it's nearly invisible, yet hot enough to glow in X-rays. This gas isn't cold and clumpy like the clouds where stars form. It's ionized, meaning its atoms have been stripped of electrons, making it nearly transparent to most telescopes. And it's not just sitting there, it's moving, threaded through filaments of the cosmic web like blood vessels pumping through the body of the universe. The challenge in finding these missing baryons isn't just their faintness, it's their temperature. The WIM exists in a Goldilocks zone between extremes. Too cold and it would clump into detectable clouds, too hot and it would shine brightly in X-rays. Instead, it lingers in a frustrating middle ground, emitting just a whisper of radiation. To spot it, astronomers have to get creative. Some hunt for subtle distortions in the cosmic microwave background, the afterglow of the Big Bang, as photons pass through these hidden gas tendrils. Others look for absorption lines in the light of distant quasars, minuscule dips in their spectra where WIM gas has absorbed specific wavelengths. But the most promising clues come from fast radio bursts, those mysterious cosmic flashes we touched on earlier. As these bursts travel across the universe, they interact with electrons in their path, slowing slightly. By measuring this delay, scientists can estimate the density of material the burst passed through. Recent studies using FRBs suggest the numbers are adding up. The WIM might indeed hold enough gas to account for the missing matter. Yet the search isn't over. The WIM structure is patchy, its distribution uneven, and mapping it requires stitching together observations from X-ray telescopes, ultraviolet spectrographs, and radio arrays. It's like trying to reconstruct a ghost by tracing its shadow. And if we're wrong, if the WIM doesn't contain all those missing atoms, then we're back to square one, forced to reconsider whether our understanding of the universe's inventory is fundamentally flawed. For now, the missing baryons remain a testament to how much we still have to learn about the cosmos. Even the ordinary matter, the stuff we thought we knew best, can hide in plain sight, woven into the fabric of space itself. And as telescopes grow more sensitive, we might finally pull back the curtain on this cosmic disappearing act, revealing the universe's hidden scaffolding in all its intricate, glowing detail. When stars die, they're supposed to go out with a bang, a supernova so violent, it leaves nothing behind but a scorched remnant or a black hole. But in the year 1572, astronomers observed something that defied every rule in the cosmic playbook. Tycho's supernova, a brilliant explosion visible to the naked eye, wasn't the end of its star. Against all odds, the star survived not as a ghostly neutron star or a black hole, but as a reanimated stellar corpse, still burning, still shining. This wasn't just a supernova, it was the birth of a zombie star. What makes this survivor so baffling? Most supernovae fall into neat categories. Type Ia, the kind Tycho's was presumed to be, occur when a white dwarf, a dense, Earth-sized ember of a dead star, siphons too much material from a companion, triggering a runaway nuclear explosion that obliterates it completely. No leftovers, no second chances. Yet when astronomers trained modern telescopes on Tycho's remnant, they found something impossible, a faint, stubborn glow at the center. The star hadn't fully detonated. Instead, it had ripped itself apart in a botched explosion, leaving behind a charred, still smoldering core. The leading theory is as unsettling as it is revolutionary. This star might have undergone a partial supernova, a phenomenon where the explosion fails to consume the entire white dwarf. Picture a firework that fizzles after the initial blast, leaving half its powder unexploded. In stellar terms, the detonation could have sputtered out unevenly, its shockwaves stuttering before reaching the core. The result, a mangled star, half dead yet still burning, its outer layers blasted into space while its heart kept beating. But there's another twist. Spectroscopic clues suggest the zombie star isn't alone. It might still be locked in a morbid dance with the companion that doomed it. Most Type Ia supernova annihilate both stars in the process, but Tycho's could be an exception. Its partner star wounded yet still orbiting the shrapnel of its other half. If true, it would rewrite our understanding of stellar partnerships, proving some stars can endure even their partners' violent deaths. The implications ripple far beyond this one star. If partial supernovae are possible, they could explain other cosmic oddities, mysterious stellar remnants that don't fit the usual categories, or strange gaps in the distribution of supernova brightness. They might even account for some of the universe's dark white dwarfs, stars too dim to spot but whose existence is hinted at by gravitational anomalies. Tycho's zombie star forces us to confront an uncomfortable truth. The universe doesn't always follow the scripts we write for it. Even in death, stars can defy expectations, leaving behind survivors where we expected only ashes. And as astronomers scour the skies for more of these undead anomalies, one thing becomes clear: stellar death is far messier, far more unpredictable than we ever imagined. Dark matter has always been the universe's most frustrating ghost everywhere, yet refusing to show itself. We've hunted for WIMP actions, even primordial black holes, but what if we've been searching in the wrong dimensions entirely? Enter unparticled dark matter, one of the wildest ideas in modern physics. This isn't just some exotic particle, it's a whole new state of existence, matter that doesn't play by the usual rules of three-dimensional space. The theory springs from an audacious question. What if dark matter isn't made of particles at all? Unparticled physics proposes that at extremely high energies, there could exist sectors of reality where matter behaves as if it has fractional dimensions, not quite solid, not quite ethereal, but something in between. Picture a cosmic substance that doesn't clump like ordinary matter, but instead spreads like a fractal, its influence seeping through space-time in ways we can't easily model. This isn't just mathematical whimsy. It could solve one of dark matter's biggest headaches, the fact that our galaxies rotate too fast at their edges without flying apart. Here's where it gets mind-bending. Normal matter interacts through forces like gravity and electromagnetism, bound by the strict geometry of our three-dimensional world. Unparticled dark matter, though, might exist in a state where it doesn't neatly fit those dimensions. Imagine trying to fill a glass with smoke. It doesn't pour like water, but it still occupies space. Similarly, this fractional dimension matter could wrap around galaxies in a diffuse haze, exerting gravity without ever condensing into detectable clumps. The implications are staggering. If dark matter is unparticled in nature, it would explain why our detectors keep coming up empty. WIMP and actions are built on the assumption that dark matter is made of discrete particles, however elusive. But if it's something more fluid, more fractional, then our entire search strategy might be flawed. Instead of looking for particles in underground labs, we'd need to hunt for subtle distortions in the fabric of spacetime itself, ripples in gravity's grip that reveal this shadowy medium's presence. Critics argue the theory is too speculative, a mathematical curiosity without experimental support. Yet proponents point to oddities in galactic rotation curves, the way stars at the edges of galaxies move as if tugged by an invisible hand. Traditional dark matter models require precise distributions to match these observations, but unparticled dark matter could naturally produce the right gravitational effects without fine-tuning. It's as if the universe prefers elegance over complexity, solving the puzzle with geometry rather than particle physics. Could we ever prove this radical idea? The challenges are immense. Fractional dimension matter would interact so weakly with our world that detecting it might require entirely new approaches, perhaps by studying anomalies in the cosmic microwave background or designing experiments sensitive to dimensional warping. But if confirmed, it would rewrite not just dark matter's story, but our understanding of reality itself. After all, a universe where matter exists in fractional dimensions is far stranger, far richer than anything we've dared to imagine. And in that strangeness, we might finally find the answers we've been searching for all along. Cosmology is facing a crisis, and its name is the Hubble tension, a stubborn discrepancy that threatens to upend our understanding of cosmic expansion. Here's the problem: when we measure how fast the universe is growing today, using nearby stars and supernova, we get one number. But when we calculate the same rate using the afterglow of the Big Bang, the cosmic microwave background, we get a different answer. These values should align. Instead, they're diverging by just enough to keep astronomers awake at night. Let's break it down. The local method relies on observing pulsating stars called Cepheids and cataclysmic supernova in nearby galaxies. These cosmic yardsticks allow us to gauge distances and velocities, revealing an expansion rate of roughly 73 kilometers per second per megaparsec. But when we peer back to the universe's infancy using Planck satellite data from the CMB, the math suggests a slower pace around 67. That gap might seem small, but in cosmology, it's a chasm. It's like two clocks, both impeccably crafted, ticking out of sync, and no one knows why. The implications are staggering. If both measurements are correct, our standard model of cosmology, the lambda-CDM framework that's guided science for decades, might be missing a crucial piece. Enter early dark energy, a hypothetical force that could have briefly surged during the universe's first few 100,000 years, altering its expansion trajectory before vanishing without a trace. Picture a rocket launching with an extra burst of fuel, then coasting, except in this case, the rocket is space-time itself. This phantom energy could reconcile the mismatch by tweaking the early universe's behavior without disrupting later observations. But early dark energy isn't the only contender. Some theorists propose that dark matter interacts with itself more strongly than we thought, subtly skewing cosmic evolution. Others wonder if the Hubble constant isn't constant at all, that expansion rates vary across space, making our local neighborhood unrepresentative of the whole. Then there's the radical notion that our measurements are being warped by colossal voids or invisible structures bending light in ways we don't yet comprehend. The stakes couldn't be higher. If the tension persists, it might demand a rewrite of fundamental physics, a new chapter in our understanding of gravity, dark energy, or even the nature of time itself. Already, astronomers are racing to test these ideas with next-gen tools like the James Webb Space Telescope and upcoming observatories mapping the universe in unprecedented detail. Every new dataset is a potential key to unlocking this puzzle, whether it confirms a flaw in our models or reveals an entirely new cosmic phenomenon. What makes this moment so thrilling isn't just the mystery, it's the humility it demands. The universe, it seems, still holds cards we haven't even glimpsed. And whether the answer lies in dark energy's secrets, unseen dimensions, or something beyond our current imagination, one thing's certain: the Hubble tension isn't just a problem to solve. It's an invitation to rethink everything we thought we knew about the cosmos. From the Great Attractor's invisible tug to eerie fast radio bursts flashing like cosmic Morse code, the universe is brimming with phenomena that defy explanation. Dark matter weaves galaxies together yet slips through our detectors like a phantom. Dark energy pushes the cosmos apart at ever-increasing speeds, a force so dominant we barely understand it. Vast voids yawn in space, their emptiness challenging our maps of the cosmic web, while rogue black holes streak through the darkness, trailing newborn stars in their wake. The Hubble tension splits cosmology at the seams, dangling the possibility that our universe's expansion rate isn't what it seems. Each mystery peels back another layer of our cosmic ignorance. The red rectangle nebula's perfect geometry whispers of stellar artistry we can't yet replicate. The moon's lost magnetic field hints at planetary dynamos unlike anything in our textbooks. Oumuamua's interstellar sprint left us wondering if we glimpsed a shard of alien engineering, or just nature's next-level creativity. Even the humble solar system guards secrets, with the Kuiper Cliff standing sentinel at the edge of our planetary backyard like a no trespassing sign etched in ice. What ties these riddles together isn't just their strangeness, it's how they expose the limits of human knowledge. The universe operates on scales and timelines that dwarf human experience, wielding physics we've yet to dream up. But therein lies the thrill. Every unanswered question is an invitation. Someone watching this might one day crack the code of Tabby's star's flickers or decode the wow signal's origin. Maybe you'll be the one to spot the next runaway black hole or find proof of unparticled dark matter's fractional dimensions. So keep looking up, stay relentlessly curious, and remember, the cosmos loves a good puzzle. If you're hungry for more mysteries, hit like and subscribe. The universe isn't done surprising us, and neither are we. Who knows, the next great cosmic revelation might start with you pressing play.